And so how this will work is we're happy to go through as many of the problems as you want, although based on like requests. So, but if over the next like minute or two, if there are any specific requests on what problems you want us to go over first, then please put them in the chat and we'll go through them first. If there aren't too many requests, we'll just go through the problems in order, but we'll start by, requests, so that if people want to leave early. Yeah, happy to start with some of the harder ones. Obviously what considered hard varies by the opinions of everyone doing the contest. So I guess the first request is for strange store. So we'll start with strange store. And then probably, I think we'll leave train and SynthClimb to later on, just because they are, those two in particular require like a little bit of like technique knowledge. The other ones should be accessible to more people. So I think we'll start with, skip through to, here we go, strange store. And I'll hand over to Isaiah, I think, who'll be running this one.
Yeah, I wrote up these slides. So yeah. So I'll quickly recap the problem just in case you didn't get off to it or you've forgotten or whatever. So yeah, obviously the statement has a lot of flavor text, but it really comes down to quite a simple idea, which is given an array of numbers, you want to determine the largest absolute sum of any subarray with the constraint that the absolute sum of that subarray must be less than or equal to m. And so m is just a number that's given in the input, so some fixed constant. And so this is the sample input that was given to you in the problem. The first number is n. First number is n, so I guess it's not really important. Second number is m, and then there's the array. And in this case, so a subarray is just a continuous subarray of numbers. So in this case, it was 3, -4, 7, and if you take this subarray of length 2, then that has a total sum of -1, and its absolute value is 1, which is less than or equal to 2, which is m, so that's fine. And you might think, well, a bigger subarray, you could get a bigger subarray by just taking this whole thing. In that case, it would be 3 plus -4 plus 7, which is 6, but that's bigger than m, so it's not allowed. And similarly, you can't just pick 7 or the 7 and the -4, because those will result in sums of 7 and 3, which are too big as well. So that's why the biggest sum you could get, the biggest absolute sum you could get was 1, or the biggest sum is less than or equal to m. Okay. Yeah, I think we're good to start moving on to the subtitle solutions. Cool. So yeah, so this notation basically just means it's proportional to n cubed. So the time that it will take will be proportional to n cubed. And for this problem, it's fairly easy to see that you can come up with some solutions that will work, but will be quite slow. One of these solutions is just try every single possible subarray. So if you have some subarray like this, so each box is a number, then you could just try this subarray, and you can just loop through all of them. And in fact, they'll be exactly roughly n squared, because you can choose n left endpoints and n right endpoints. So you just loop through your possible left endpoints, possible right endpoints, sum all the things together, check that the absolute value is less than or equal to m, and if it is, store that into your answer or your potential maximum answer. Hopefully that's clear. If there's any questions, feel free to ask them at any point. Yeah. So the next solution, you can slightly optimize this. So one thing is that if you're looping over, say, your left endpoint as your outermost loop and your right endpoint is your innermost loop, then you'll consider the ranges like this. So you consider that range, then you'll consider that range, then you consider that range, the first 3, then the first 4, then the first 5. And it's pretty easy to see that these ranges are very similar to each other. In fact, they're just one element at each time. So in your loop, you can just, rather than calculating like the entire range sum each time, you use the previous result to be a bit faster about it. Hopefully that way of thinking about it's clear. And because it's useful for the next solution, I'll present a slightly different way of calculating for the O of n squared. Yeah, if we could just go back to, yeah. So another slightly different way of thinking about it is you create a prefix sum, and I'll very quickly explain it. A prefix sum is an array. So an array such that each value in the prefix sum is the value of all the elements to the left of that position. So for example, prefix of 3 would be the first 3 elements in the array. Depends on exactly how you index it, but that's the general idea. And so if you keep track of the sum of that array, the sum of that array, sum of that array, and so on, then to calculate the sum of a certain range, I'm running out of space here. But to calculate the sum of a certain range, like for example, this range, you can just take the sum up to this element and subtract the sum up to this element. So more precisely, the sum for like the sum of a range like that, or like that, is going to be prefix of R minus prefix of L minus 1. Sorry for this pretty dodgy writing. L minus 1. Close bracket. Cool. So in that way, we can instantly calculate the sum of each range rather than having to loop over each of its elements. So that's how we can make it slightly faster. So that will take time only proportional to the number of pairs, which is n squared, because you can calculate the sum of each range instantly, or the sum of each pair instantly. Okay, so now we move on to the full solution. So with that in mind, we can actually just reframe the problem as, once we've calculated the prefix sums, we want to find the largest difference between any two values in the prefix sum that is less than or equal to n. So if you have a prefix sum, if your prefix sums are like -3, 2, 1, 5, these are just random numbers. So the sum of the first 3 elements is -3, the sum of the first 2 elements is 2, the sum of the first 3 elements is 1, the sum of the first 4 elements is 5, and the sum of the first 5 elements is 6. Then all we're trying to do is find 2 numbers such that the difference is as big as possible but less than or equal to n, because then we'll have a range such that prefix of R minus prefix of L is less than or equal to n and as big as possible. So instead of finding sums of subarrays now, we're just finding differences between 2 numbers in the array. So one way to do this is, how have I written it? This solution is actually not the full solution yet. So I'll just skip over that one because I've already skipped over it. So can we go to the next slide, I guess? Yeah. So once you have your prefix sum array, so just ignore that dot point. I won't go over it now, but you can think about it if you're interested. We're trying to find the biggest difference that is less than or equal to n. Now, the biggest difference between 2 numbers, there's a few ways to do it. One of them is to sort the list. So in this case, I think it was, I'm doing it at the top, 1 or -3, 1, 2, 5, 6. And you can kind of see if we start our thing over here, then if we want to stay under m, then there's some right endpoint that we have to stay under. So if m was like 8, then we could go at most here, because we can't go any further than that, because then our sum would exceed that. So if we take 5 minus 3, then we don't exceed 8, but if we go to 6, we exceed 8. So a way to keep staying under 8 and calculate the rightmost point for each. So yeah, I skipped a bit there, but for each left endpoint, if we want to calculate the biggest sum, the biggest range that begins at that left endpoint, then we want to calculate the biggest sum, the biggest thing on the right that will keep the difference under n. You can kind of see it for -3 it goes to 5, and then when you shift over 1 to here, it will shift the right endpoint possibly some amount, maybe not the same amount, could shift it like 2 positions, could not shift it at all. And this way you can kind of sweep along. So if you look at my camera, you can see if you move the left endpoint, then the right endpoint will move a bit, left endpoint, right. And the important thing is that as the left endpoint moves 1 square, the right endpoint will always increase a positive or a non-negative amount of squares. So we can always keep track of that. There's other methods other than that, like binary search, that will also work. Now, one thing is that in this thinger, we need to actually guarantee that R is bigger than L, because otherwise we'll have a backwards range. And an interesting fact is that originally we designed this problem, and this was not absolute value, it was just sum. And this meant that it required some effort to make sure that R is greater than or equal to L. But actually, this is actually, the absolute value actually makes the problem easier, because if you have a range that is negative, if you have something that's backwards, like you try and sum up prefix of R minus L where R is less than L, you're kind of summing this range minus summing a smaller range and subtracting a bigger range from it. This actually means you're calculating the negative sum of that range. So in that way, you actually have calculated the negative of that range. And so if you just do this thing and ignore the fact that R must be greater than equal to L, then you actually consider all subarrays, all negative sums, like the negative of each subarray sum and the positive of each subarray sum. And so in that way, you'll calculate the largest absolute value sum. So there are quite a few steps there. And I guess just because of how people chose the problems, that was the first one we went over. So I'm happy to take any questions because there were quite a few steps there. So let me know if there's anything that people were bothered by. Otherwise, yeah, this problem does admit a lot of solutions. Yeah. So if you like read in the array and you don't pre-compute anything, you'll probably have to use something like a set or a segment tree. But if you pre-calculate and sort, then you can use 2 pointers, and that does it quite nicely. So 2 pointers is a technique that shows up fairly often, and it's one of the more intuitive techniques that you'll see. And that's just the idea of moving the left pointer continuously and moving the right pointer as much as it needs to, or vice versa. You can flip it, you can frame it in some other ways. All right. If there's no questions, I think we're happy to move on to another problem.
All right. If there aren't any more requests, I guess I'll go and do the 2 last problems since that's what's wanted. So I think cylinder, let me just clear off all these drawings. Okay, so in cylinder climb, you're given an RBC grid with point values. You want to find the maximum walk that like starts at the bottom of the grid, like starts here, for example. It walks up, and then you can only move up, left, or right, but you can wrap around. So you can go from this side, then across to this side like this. But you can only visit each cell at most once, and your path, the sum of your path, the sum of the values you visit. The question is, what's the maximum path you can make? So for example, we go like across like this, follow the arrows, we get a total sum of something, which is the maximum. Happens in maximum in this case, if we follow the green ones. And so it added together all the values. That's sum of our path. And the question is, what's the biggest sum of the walk you can find? And so we're going to use dynamic programming to solve this problem. If you don't know what dynamic programming is, this is covered, I think, in 3121, I think. I could be wrong. But it's a technique where, 3121, yeah. It's a technique where you compute the values for like a small subproblem, which is to solve the overall problem. And so how dynamic programming works in this case is we're going to first go over a slower solution. So your state is the row and the column. So we have our grid, and our state is the cell we're at, defined by a row and a column. So like an IJ, where I is the row and J is a column. That could be this one here. And the answer to dpij will be the maximum walk starting at ij and finishing at the top. Now, if you start at ij, then what you can do is your possible moves are you can walk some amount to the left or to the right and then walk upwards and then keep going. So like the answer for dpij is the maximum. So dpij is going to be the maximum of, well, let's say we walk to cell ik. So I is the row. So like when you're walking to left or right, you stay on the same row. So you're going to walk to some other cell, let's say ik. So it's going to be dp of ik plus the sum of all the values from I to k. This could be either left or right. There's two options. So let's say this is IK here. You could either walk this way or walk the other way around. Plus, like the best path to IK. So the best path to IK. That's either walking left or walking right. Plus then dp of I, if we number the rows going down from the top, so if this is like row 0, row 1, row 2, row 3, then it's dp I minus 1k. Because dp I minus 1k is the best walk starting from this cell here. And so at ij, we consider which cell do we walk along in our current row, and then we walk up and continue our walk. And so we can compute dpij by considering each other k on our row, finding the best path from I to k, and then adding the result of that state. And so the complexity of this depends how you do it, but kind of naively, there's order r times c states, but how many possible IKs are there? Well, for each like state ij, there's one k for every column. So multiply by c again, so you get r times c squared, which is too slow, unfortunately, to get full marks. But this will get you, I think, a generous number of partial points. I don't know the exact number, but it's a generous amount of partial points, I think, on this problem. Maybe 50%. I can't remember the exact bounds. It did say in the statement.
Seems like 60%.
60%. 60%. Okay, which is pretty good. But we can do better than that. And how we do better is by kind of a smart optimization. We're going to compute the DP value for everything on the row at the same time. So we're going to assume now that for a given row, we've already computed the DP values for the row above. And now we want to compute the DP values for everything on a given row, all at once. To do that, we're going to have to do a few different passes because there's a few different options. Let's consider, I'm going to divide broadly into 4 cases. Which I'm going to write at the top actually to give myself space. So there are going to be 4 cases. The first option is we walk right and we don't wrap around. So by this I mean, we start like, this is like our row like this. If we start here and we walk to here, then we've walked right, we haven't wrapped around. Case 2 is we walk right and we do wrap around. So in that case then, that's the case where we start here, for example, we walk, wrap around, and then we keep walking. The other 2 cases are just the same thing, except we walk left instead of right. I'm only going to, for now, solve the case where you walk right. Solving where you walk left, it's the exact same solution. You just kind of flip around some stuff. But if you can solve it for the case where you walk right, then to solve the case where you walk left, you do the same thing, just loop backwards instead of forwards or something like that. So the case where we walk right and we don't wrap around, this is perhaps the easiest case. And to do this, we're going to utilize a little bit of prefix sums, which is what Isaiah described for the last problem. So let's say the values in the cells are like 5, 3, 2, 1, 6. So these values are like, I'm going to draw them in the cells to make it clearer. 5, 4, -2, -3, 1. Then the prefix sum or the cumulative sum is going to be 5, 9, 7, 4, 5. So that's just the sum of all the values up to that point. So this 7 is 5 plus 4 minus 2. So each value is just a sum of all the values leading up to it. And why does that help? Well, let's imagine that we also have the DP value for DPI minus 1. So that's the DP value for the previous row. So call these values here call them the prefix sum. So prefix sum of K is the prefix sum in column J. and this is dp of like I minus 1k. And these values might be, I don't know, 2, 6, 3, 2, 1. These are the best walk starting one row above. Then if we want to find the dp value for undo dp I5, so I'm going to work out the dp value for this one here in the case where we're going to be walking right. Let me think about this for a second. My bad. Imagine the case we're going to walk left. Sorry, we're going to walk left, not walk right. The case where we walk left, and we want to work out the dp value for like this cell, for the last cell. So we want to work out the dp value for like this cell here, for example. Then if we walk left, then we could have ended up at any of these positions. And in fact, the total sum of doing this, we can use a prefix sum plus a dp value here, is going to be, well, the dp value, which is 3, plus the sum of everything, which is 5. That's the last prefix value. That's the sum of everything in the row, minus this 4 here, because we don't, minus 9, not 4, minus 9. This prefix sum value here, because we don't visit the first 2 cells in the row, which overall you get 8 plus 9 is 17, which corresponds to like 3. No, you don't get 17. You get -1. I can't do addition. This corresponds to this 3 plus -2 plus -3 plus 1 is equal to -1. And that corresponds to this dp value minus this prefix sum value plus the last prefix sum value. And so then if we compute a new value, which will be the dp value minus the previous prefix sum value. So I'm going to put that down the bottom. It's going to be dp I minus 1k minus the prefix sum of k take 1 in green. That is then going to be margin prefix of like 0 is 0. So for the first one, we get 2 minus 0 is 2. Second one, we get 6 minus 5 is 1. Third one, we get 5 minus 9, 3 minus 9, which is -6. Here we get 2 minus 7, which is -5. And here we get 1 minus 4, which gets us -3. Then the dp answer for this final value here is just the maximum dp value out of all of these, which is 2, plus the sum of the entire row, which is 5. So you get 2 plus 5 is 7. And that 7 with optimal dp value for this last one here, which corresponds to walking all the way to the end and then walking up. So we've essentially used prefix sums to speed up our dp recurrence. And so as we loop left to right, we can keep track of the best value of dp I minus 1k minus prefix of k minus 1. We keep track of the best one as we walk along, and then we add the prefix sum value, and this will find the dp value. So of only considering the case where we walk left first. If that doesn't make sense, let me know. It's a fairly involved idea, but the basic idea, I'm going to clear my screen for more space, is we consider the case where we walk to the left first, and to do that, we loop from left to right, and we keep track of essentially the best option as we go along. And as we keep walking, the best option will update. And that considers the first case where we walk to the left and don't wrap around. For the case where we walk to the left and we do wrap around, it works out to be a very similar thing. It just, the details change a little bit. So if I'm going to draw out a grid again. So in the case where we walk to the left and wrap around, then we start here and we wrap around like this. In this case, the value for this cell, well, if we think of it in terms of prefix sums, if we add the prefix sum for everything, and then minus the prefix sum for this cell here. So we add that in green, we then minus that, which if we subtract this prefix sum value, that subtracts all of these values here. And then we add back the prefix sum value at the cell. We add back this. Then we'll get precisely the values that we want. And so
I think Angus just cut out for the last 10 seconds, unless that was just me. Yeah.
Yep, I cut out. I'm not sure what happened there. When did I cut out? Not very long ago?
Like 10 seconds or 20 seconds ago.
Oh, easy. So it ends up being, so I'll go explain that second case again. Second case is where we walk from left to right. So right to left, we walk to the left, we walk right, left, and we wrap around like this. So in this case, then, if we want to work out the DP value for this cell here, if we're walking to the left and wrapping around, that means our possible final cells are any of these ones here, because we've walked to the left and wrapped around. And so in that case, if we get DP I minus 1 K, and then we subtract prefix of K minus 1. So if we loop backwards from right to left and keep track of the best value of this across all K, then if we get the maximum value of this across all K, and we go plus DP plus prefix of J, plus prefix of J, and then we also add prefix of N, that's of C, that's the entire prefix sum, then we'll get the correct value. Why is that? Well, imagine this is K here, this is J, then we're looking at, well, prefix of J, that's the entire, we're adding the entire row together. We're then subtracting at K minus 1, so we're subtracting all of these values, and then we're adding back these values here. So in total, we add this value once, add this value once, don't add this value, and add these value once, which corresponds to all the cells that we visit. And so we loop from right to left and maintain the best value of this. And we take that, and that's our answer. So, and we do the same thing for walking from right to left instead of left to right. It's exactly the same thing. And so if we do this, then we can compute an entire row's DP values in order R. And so overall, we're left with an order R times C solution. I told you at the start this would be a complicated solution, so you were warned. But yes, that is a solution to this problem. It is quite involved. Let me know if there's any questions about it. But the idea is to order RC, and we use prefix sum to do the recurrence efficiently, which is what I went over in some more detail. If there are any questions about that, which there might be because it's quite an involved solution, please let me know. If not, I'll hand over to Isaiah to do train network. I think that was the only other one there was demand for, I believe.
Yeah, sure. Yeah. Hopefully people are still interested in train network because a few people have left. But anyway, let's do train network anyway. So this one is also requires some relatively advanced machinery, not DP this time, but as a graph problem, it's kind of natural that it does require something a bit harder. So yeah, the question obviously doesn't, well, not obviously, but it doesn't mention anything about graphs, but it's easier. Hopefully most people here are familiar with graphs. And if you're not, it's basically a picture like this. So you have your stations and your railroads, as I said in the problem, and they each have a weight. And the question is, you want to travel from node 1 to node 6, or node 1 to node n. travel from here to here. And you want to use as little money as possible. And the amount of money that you spend is the sum of the two largest weights. So that's where the problem is interesting, the sum of the two largest weights. So more classical problems would be like the sum of the largest weight on it. Even more classical problem would be the sum of all the weights on it. In this case, the sum of the two largest weights on it. So in this case, the best way to do this was to follow the red paths. And in this case, that costs 1, and that costs 4, and that costs 1, and that costs 1. So the two most expensive ones are 1 and 4. Doesn't matter which one you pick because it'll be 1 anyway. And 1 plus 4 is 5. So the answer is 5 in this case. Oh, my pen is quite bad. Now, you can look at some other paths, but they're not going to be as good. Like you could think of the path 1, 1, 1, 3, 3. That would also get you from 1 to 6. But then the two most expensive would be 3 and 3. And that's 6, which is bigger than 5. So it's not optimal. So the question is, what is the cheapest sum of two largest edge weights on a path from 1 to 6? Hopefully that's clear. Okay, we can now start talking about solutions. So yeah, it's useful to discuss the slow solutions first. So as with most of the problems today, you could probably get, you got a decent amount of points just for doing a somewhat brute force solution. In this case, one brute force would be to try every single pair of edges. So so loop over each first edge in the graph and then do another loop inside that, which loops over every second edge of the graph. And you want those to be the two largest edge weights. And so that means that every single, so if you've fixed your two biggest edge weights, then every single other edge must be less than or equal to the smaller edge in that pair, or the cheaper edge in that pair. So cheaper than both edges in that pair. So I guess quickly go back to the previous slide and I'll explain how that works. So for example, you could say, I want my biggest two edges to be this and this. Well, then what you want to do is check if you can connect 1 and 6 using only these two edges and stuff that's cheaper than both of them. So only stuff that's cheaper than 2. So the stuff that's cheaper than 2 is that, and yeah, that's it. But so we failed to connect 1 and 6. And how you would check if they're connected is just a classic problem, which is just a DFS or a BFS or whatever. But a DFS is easy. If you wanted to try, so you'd fail to connect them in that case. If you wanted to try these two edges, then you'd want them all to be less than 2 again. And in this case, you'd be able to do it because you can use any of these edges. And in this case, there exists a path using only these edges. But this one wasn't actually optimal. So the optimal one was to pick, say, this edge and then you could only use stuff that's less than or equal to 1. So use that and that. In that case, do 5, which is the best you can do. Okay, so that's the n cubed solution. So for the n squared solution, there's quite a lot of ways to think about it. But this solution, as well as the full solution, basically involve optimizing this idea of selecting a maximal pair of edges. So one way to do it for n squared is to try every edge as the most expensive. So instead of trying each pair, you just pick one of the edges and you say, this one is one that I want to try and make the most expensive edge. And if you want that to be the most expensive edge, then you have some kind of graph here, your most expensive edge here, and some kind of other graph here. And say this one contains n, and this one contains 1. The left one contains 1. So these are like weird subgraphs, and I guess you could have edges connecting them as well. So that's your maximum edge. Now, if we want to make our maximum edge, then firstly, we can only use edges that cost less than or equal to it. And secondly, we want to minimize the other edge. We want to minimize the other maximum edge we can select. Now, yeah, I think probably the easiest one to understand intuitively is binary search. So we say, does there exist a path using only stuff below this edge weight, and given a certain maximum edge? So we use that maximum edge in anything below that certain edge weight. But other solutions use minimum spanning trees and prims. And prims is quite nice because basically what you're doing is finding a tree of paths that are have the minimum maximum edge cost. So this is a pretty dumb phrase that I invented. I don't know if there's a more standard way of saying it, but it's basically saying we're trying to minimize the cost of the largest edge on any path. So if we fix this edge, then from 1 to n, change color, from 1 to n, we want to minimize the maximum cost along there, and we want to minimize the maximum cost along there. And to calculate these, we can actually pre-compute them. So prims will do this nicely. Prims will, you can Google it, but it's, I don't know if this is helpful or not, but it's very similar to Dijkstra, except instead of sums, you use minimums or maximums or whatever it is. So prims will like find a tree, and to do this, it adds, instead of adding to its queue distances, it adds the minimum weight. So it will search stuff in order of the smallest minimum maximum edge it can find, and it will gradually add more nodes that are harder to get to. So you'll have some kind of tree, and each of them will have a minimum maximum edge cost from n. And same for 1, you'll have another thing from 1. And this will reach every node. It wasn't said here, but in the problem statement, it said that the graph was connected. So any 2 nodes can be connected by some path. So this will reach every node eventually, prims in particular. And so once you've done that, so you can do that as your pre-computation step. And then to check every edge, you just check, can I connect? So how much, so what's the minimum maximum edge I can connect to? And what's the minimum edge I can connect to? Now, an important, I think it's still important in this case, caveat is that you have to make sure that the minimum is less than this weight. Because if the minimum is greater than this, so if the minimum to get from 1 to some node is bigger than this one, well, for this entire idea to work, we claimed that this was the most expensive edge along the path from 1 to n. So we can't actually use that if the minimum along this path is bigger than this weight. And in fact, if there was any, if that was the minimum we could do, then there's absolutely no way we could make that the maximum edge, because we can't get smaller than it, because this was the minimum. So you can't actually get any smaller than this, and then you can't get any smaller than that. So you need to add that check. And yeah, I think I just described the full solution. I don't know how I ended up doing that, but basically to get order n squared, you just do it a bit less smartly than the full solution. So I think I pretty much just said what the full solution was. So I don't exactly know what the n squared solution is, but I'm sure it exists. So yeah, just to reiterate, I guess, pre-calculate using prims. You can also DFS over the minimum spanning tree. That does the same thing. Try each edge is the most expensive. It's only a valid expensive edge if it's bigger than both sides. So yeah, I guess the difference is that you're calculating both ways in this one, in your pre-computation. So if you claim that this is your maximum edge, you can't just always use it as your maximum edge. You have to make sure that it's bigger than any minimum path along here, or the minimum path along here by maximum edge cost, and the minimum path to get from here to n along the minimum edge path. The minimum edge path, the minimum edge cost of that path, the maximum edge cost of that path, the minimum that you can make the maximum edge cost of any path from that node to n. Okay, so I think that should hopefully be enough to possibly understand the solution. Clearly, I've got myself a bit confused about the details. It is quite tricky, just because of all the minimizations flying around and making sure that you don't find an edge that's invalid. Because you have to be careful. If you say this is your maximum edge, but it's actually really tiny, and then you find an edge that's bigger, and then you claim, oh, I can find a small edge, I can find a small path with a small minimum here, and apparently this minimum is this apparently maximum edge is actually really big, or it's actually really small. In that case, you'll say that you can get a smaller answer than you actually can. So that's what this sentence is saying, basically. So hopefully that's enough details to potentially be able to implement this problem if you want to at some point. Let me know if there's any other details. Otherwise, we'll move on to another question.
Is there any other requests? I think, unless I missed anything, these were the only problems that people requested in the chat. I might do a couple of the other ones for the recording, but are there any demand for any other questions? If not, a couple of other nice ones. I might go over gradient. That's a nice problem. Gradient. Okay, this one shouldn't take too long. And I think for the people who have been very confused by the previous problems, this one should be a breath of fresh air, I hope. And for anyone watching the recording as well. This one should take less time than the previous problems. It has quite an elegant solution in the end. So this one is you're given endpoints and you want to find the largest gradient of any line passing through 2 points. And there's up to 200,000 points. So the obvious idea is just try every pair of points, calculate their slope, just like rise over run, and then find the biggest. But that's going to be too slow with 200,000 points. But there's like one quite smart observation, and that is consider 3 points sorted by their x coordinates. Like this, or we can consider well, these ones work, or even like this, for example, and consider the lines we can draw between them. We can draw like this line, this line, this line, and then the lines between the outside points like this. And I've drawn them in different colors on purpose. And my claim is that in any case where you have 3 lines, the blue one's not going to be the biggest one. That is because one of these 2 intermediate slopes is going to be at least as big as the blue one. The only case where they're equal is if the 3 points are collinear. So if you have the case where you have like 3 collinear points, then that like this case here, then all 3 slopes are equal. But in any other case, you're going to have one of the 2, or sorry, the blue slopes didn't appear in here. I must have got rid of them. But like the green slopes are always going to be, one of the green slopes will always be bigger than the blue one, and one of them smaller, except in the case where the 3 points are collinear. And that is because imagine both green slopes were steeper than the blue one, then like it just wouldn't work, because then you'd need like your 2 green slopes would be like this, and then your last one would be like a lesser slope, and then it obviously wouldn't connect the 2 endpoints, so it doesn't work like that. My lines are disappearing that I'm drawing. Not sure what's going on with annotation, but the idea is that, yeah, if both intermediate slopes were bigger, then the final slope would not connect the 2 endpoints. And because of that, you can then apply proof by contradiction and see that the answer will be between 2 consecutive points when you sort them by x coordinate. Because imagine the answer wasn't between 2 points sorted by x coordinates. Like the answer was between like these 2 points here. Well, we just proved that one of these lines is bigger. So obviously our original one was not the maximum slope. And so that leads to a very nice solution where you just sort the points and compare adjacent points and find the slopes. And then we're computing only n-1 slopes and we'll find the answer. There's been some talk in the chat about precision. Yes, there was one annoyance, which was that the templates weren't the best with precision. There's no, yeah. So that was the annoying part, but yeah, so you have to be careful with that. We put a note in the problem for that, but I think that was missed at the very start of the contest. Yeah, so there were some issues with that. You had to print the output to 6 decimal places, and if you weren't careful, that led to some issues. In like C, if you go like %.6 LF, this prints a double to 6 decimal places. In C++, you use like set precision or something like that. Set precision, like 6. I think that's sig fig, so you do like 10 there or something, and it will pass. In Python, I think it's all automatic for you. So yeah, you have to be careful with precision, but otherwise the problem's not too bad. Yes, let's just work backwards then. Should you connect 4? Is there any demand for connect 4?
Or any other problems?
Any other problems? Yeah.
Happy to go over any problems.
Yep. Connect 4. Okay. As I'll go do connect 4 then.
Yeah. It's just an interesting point about gradient. Took me and Angus and Joseph, I guess, I think like a day or two to realize that you could actually do it nicely. We originally had the problem and we thought it was really hard. We thought you needed to do some kind of weird geometry tricks or some segment tree, similar inversion counting kind of thing. But in the end, Angus eventually discovered while writing the data that you could just do it really nicely by sorting the points. And so that's how that problem came about. And I think you'll probably agree that it's really quite hard to come up with that observation, which is why we put it relatively late in the contest, even though the implementation is about 5 or 6 lines in Python and probably a similar amount of lines in any other language.
Yeah.
All right.
The
So
original
connect 4.
solution. So the original solution was if you binary search the answer and then like it becomes like inversion counting. And that was like the last question in the contest. But then I was writing the data for it and I was like, okay, what's a broken solution? Just compare adjacent points by x coordinate. I was writing data and this solution was passing every test case. And I was like, hang on, this is kind of sus. And I thought about it and was like, oh wait, that solution's actually correct. And then it became suddenly was moved down the ranks. So yeah, it's a neat trick, but not easy to spot.
Yep. But a few people did solve it during the contest. And I don't actually know how you would come across that observation naturally, but so yeah, I guess I'm kind of impressed that some people did, but I'm sure you would find it eventually if you try enough things. All right. So we'll get on to connect 4 now. So yeah, all good. Yeah, so yeah, Ollie's mentioned a nice solution, which is probably the easiest one to come by. I'll quickly go over the problem though. So yeah, I think I lagged a bit in Zoom, so hopefully I'm back now. So what I was saying is I'll quickly go over the problem. So you're given a connect 4 grid, which is 6 by 7. I think that's what you'll get if you look up the official rules or you whip out your connect 4 board from your cupboard. And so you're given a 6 by 7 grid, so six rows and 7 columns. Sorry about that top row. That's just how the slides happen to be. Each cell is either empty, red or blue, and you're going to place red tokens or whatever they're called in some columns. And you want to output the sequence of moves that allows the red pair to win in the minimum time possible, or minimum number of moves possible. So in this case, it would be nice if I colored the sample, but whatever. In this case, one best way to do it is to put a red there and a red there, and that will create a vertical thing there. Another way is to my undo button is really slow, is to put one there, and that creates a row of 4 there. So, and you output 5. So 5, 5 means you put one in that column and you put one in that column again, and that means you get a stack of 4 there. And you can output anything if there's multiple of the same length, but you have to output one of the minimum length if you can. Now, I guess a weird thing about the problem is that there's a cap on the top, and this makes implementation a bit annoying, and it means that there's some interesting cases. In particular, there's cases where you can't actually complete the board because, for example, if the whole board is full and no one's won yet, then you can't win because you can't do anything. And I think the samples indicated that anyway. But yeah, that is a minor annoyance, I guess. So now I'll get on to discussing the solution. So yeah. So as Ollie just mentioned in the chat, I think a little while ago, you can try every consecutive 4. So if you have your grid, you try there, there, across, whatever, to all of them. And there's not very many of these, so that's fine to just loop over and see how many moves it requires to form a 4 in a row there. Now, yeah. the thing you have to do first is check if that's actually possible. So to check if it's possible, you just check that there's no blues in the way. If there are reds already there, then that's great. That's helping you. If there are dots, then you can fill it up eventually. And something I didn't mention was that you're guaranteed that the Connect 4 grid like obeys gravity. So that means there's no floating pieces. And so that means if you have any empty cell, that means they'll have nothing above them. So that means if you have an empty cell, you can always get a red cell eventually into it. So say these three are empty, this one's blue. You can eventually get a red cell into this square by filling up those two first. And so that just means to get the minimum moves for each empty cell, so for each non-red cell and then a non-blue, because otherwise it would be impossible, you add one for the difference between the original and final height. So the original height it was and the final height you want to be. So to go back on this little example here, say you're trying to get the 4 in a row that goes like this, and there's an empty cell there. Well, that's kind of clear what I'm trying to say. So in this case, there's this empty cell here, which we have to fill up with the red, this empty cell and this empty cell that we have to fill up with the red. So in that case, that adds 3 to our score for that particular cell of this particular arrangement that we're trying to achieve, that 4 in a row. So we're going to just try all of them. In the column case, you don't exactly subtract the heights, you just kind of work out how many you need to build up. And in fact, in the column case, you can just do that separately, because in that case, you're just looking for the maximum number of consecutive reds on top. So the column case is kind of a bit different because you don't need to build up each time to each thing. Now, so that's one solution, which is just try every single possible location, check if it's possible, and then calculate how long it takes. Alternatively, this one's they're probably roughly similar to implement, I guess. This problem is just kind of a lot of implementation, because like as opposed to the other problems, it's more about, it has a lot more to do with just implementing it and implementing kind of weird games with quite specific constraints rather than solving much problems. But I guess the problem solving aspect is making sure it's efficient enough. So I haven't looked through the solutions that carefully, but some people might have tried a thing where they just try recursively doing moves, which is quite a natural thing to think about when you have a small kind of game to play. So that just means you keep track of the moves you've made so far, and you just keep branching out into every possible move sequence. So say you put a thing here, and then you put a thing here, and you put a thing here, and you keep doing that until you reach a dead end. And then once you've exhausted all of that, you go back to when you just put a thing here, and you put a thing here. And that's a pretty crappy explanation, but that's the basic idea. You just exhaust all sequences that way. Now, I think the data was designed, or just the nature of the problem meant that doing this naively would not quite work. It would be too slow. So one thing you can do is observe that the order that you place the pieces doesn't actually matter. So that means you can just place them in ascending order, which means in your recursion, you don't want to place the piece to the left of a piece you've already placed, or to the right. Just stick to one of them throughout your code. So yeah, make moves in columns in non-decreasing order. And equivalently, we can try every possible number of moves in each column. So we can define like a sequence of moves, instead of by defining it by like 1, 2, 3, 1, 2, 5, or whatever we do, we can just define it by, for each column in the grid, how many things do we put in it? So say we put 0 there, 1, 2, 1, 0, 0, 0. And in that case, so this recursive solution, and also just exhausting every possible number of these, will actually do exactly the same thing. I don't think you even need to be clever about exactly how you cache anything. You probably don't even need to cache anything in this recursion. So yeah, so those who are interested, the time that could take, you could just implement this and be happy you'd get it right. But if you want to now analyze how long it will take, that's 6 to the 7, because each of these could have up to 6, because you never want to place more than 6 in a column, because that is the height of the column. So that's 6 to the 7. I think the pen's blocking it. There, 6 to the 7. And then the 6 times 7 is just for the grid. And yeah, if anyone knows what big O notation actually means, this is an absolutely terrible piece of notation, but hopefully it's clear what it's actually saying. And so I guess I made a sentence. Apparently, big O of 6 times 7 times 6 to the 7 is a sentence. So yeah, not a great line of writing by me, but yeah, that is 2 solutions to the problem.
Okay. Is there any
Yeah.
demand for any other problems? Otherwise, we'll just keep going backwards in backwards order until we get to, before we stop at the star problem. All right. Should we go over ingredients then?
Sounds
All
good.
right. I'll clear the screen. There we go. So this problem was perhaps an interesting problem, kind of unique out of the problems here. In this one, you have like n ingredients listed. So you have like the PI values, which is the percentage of each ingredient. Initially, these values were non-increasing, so they're kind of decreasing order, but there can be ties. Each value is a positive integer, and they all sum to 100. So they could initially be 50, 20, 10, 10, 10, which is the percentage that each ingredient makes up the entire food. And they add to 100, obviously. However, some of them are missing. So -1 means the value is missing. And the question is, you just fill in the missing values such that it's valid or show that it's impossible. So if you're given 50, -1, -1, 10, -1, if you fill it out like this, that's correct. Alternatively, this also works. If you're given the input case like -1, 60, then obviously you couldn't solve this case because this first value must be 60 or more by the first rule, but they must add to 100. And so it's impossible to fill this in with a number so that all the rules are followed. So this case would be impossible. So the idea is for each value, there's a maximum and a minimum based on the values to the left and right. So in this sample case, which is 50, -1, -1, 10, -1, we know that these two -1s at the start are somewhere from 10 to 50 and 10 to 50. And this one is from 1 to 10 based on the values around them. And so we have like possible options. And what we do is initially we give every value the biggest thing we can. So we go 50, 50, 50, 10, 10. And we add them all up and we get 170. Now, if this was equal to 100, we're finished. If this was less than 100, then it must be impossible. Because if we assign every value the biggest we can, and that's still less than 100, then clearly it's impossible. And then if we then assign every value its minimum possible value, like 50, 10, 10, 10, 1, if we sum them together, we get 81. If this was more than 100, again, it would be impossible because if the minimum possible values sum to more than 100, then it must be impossible. But if the maximum values sum to more than 100 and the minimum values sum to less than 100, then in fact, it is possible to do it. And I'll describe how to do it now. So we're going to start with every value being the maximum possible value. And then we just decrease values until it works. So we go from right to left, and all the values we can change, we decrease them. So we decrease this first value down to 1. So we set this to a 1. And the sum is still 161. So 161 now. That's still bigger than 100. So then we go here, this value here, and we decrease it down to 10. So we get 10 here. Again, it's still valid, obviously, but it's now up to 121. No, 121. And then we get this last value, and we don't decrease it all the way because that'll make it too small. Instead, we decrease it just to the right value. So the value it needs to be is, 100 minus 71, which will get us to 29. Am I off by 10? 19. 19? 29. Something like that. 30. Yeah, 29 is correct. Okay. And so we give it that value and it works out being correct. So first loop from left to right, we give everything the biggest value possible. We then loop from right to left and we decrease values while we can. And eventually we'll get to a solution. Because we'll just keep, if we decrease values one at a time, then we'll keep decreasing them until we hit a sum that's 100. Because if we keep decreasing values all the way, eventually we'll be left with like our minimum solution, which we already checked had a sum less than 100. And so by like, I guess a discrete version of the intermediate value theorem, because we're decreasing values by one at a time. If we bring them down one at a time, then eventually we start above 100, we finish below 100, and we decrease by one at a time. Eventually, we'll hit a solution that has a sum exactly 100. And that will be the answer. And if this solution fails to find an answer, then that must be the case when either the maximum is less than 100 or the minimum is more than 100, in which case it's impossible. But yes, that is the solution. We just loop from left to right, making everything as big as possible, and then from right to left, making things smaller until it works out. Okay, if there aren't any questions, we'll go to Domino's.
Yeah, feel free to ask questions because I'll talk about something a bit unimportant for now, and that is that ingredients is inspired by a real world problem. I have this pack of popcorn here. I don't know if this is going to be legible. Focus.
I think it thinks it's part of your background, and Zoom background is like getting rid of it.
Background. It's the most important part of the talk. There we go. Ingredients. Yeah, you see that this pack of popcorn has popcorn, coconut oil, and salt, but only the first one is labeled as an ingredient, which is kind of interesting. I'm the kind of person to notice that. And yeah, so just then I Googled what are the requirements around percentage labeling, and apparently if it's like a key component of the food, you have to give it a percentage. So it's not just like randomly they remove percentages like we did, but yeah, interesting piece of trivia, I guess. All right. Yeah, feel free to Google it and read some 23-page document about the laws around labeling food in Australia and New Zealand if you. So yeah, dominoes. Given a sequence of dominoes in a line, each with a weight, determine the minimum number of pushes to knock them all over. So yes, some dominoes in this order, and they each have a weight. So I'll draw it a bit bigger so I can actually do it nicely. Seems like my pen is kind of clear now. So each one is a weight, and you're going to push them either left or right. So you're going to pick a domino and push it either left or right, and it's going to cascade until it cascade and only push stuff over of lower or equal weight. So for example, in this case, we can push this 3 to the left, and that knocks over all of these 3. We can push this 2 to the right and knocks over that 2. We can push that 10 either way, whatever, doesn't matter. And then that costs 3 operations, and that was the smallest we could do in this case. Yeah, I think that should be fairly clear. Yeah. So yeah, onto the solution. So this isn't necessarily necessary, but a way of reframing the problem is to decompose the sequence or reframe the problem in a different way. So instead of pushing dominoes and they knock over stuff of lower equal weight, we're saying we always push to the right, and when we push, we can either pick it to go in the positive direction or the negative direction. So let's see if I can get my thingo back. Yes, so yeah. So alternatively, we can think of the problem as we push over this weakly increasing sequence, a non-decreasing sequence. Then we push over this decreasing sequence or weakly decreasing sequence, and then we push over this weakly increasing sequence or decrease. It doesn't matter for the last one. So that makes it slightly easier to think about, and that means we can just process it from left to right. So once we've thought about it like that, we can just think about it. We can just write a solution where we keep track of whether we're in an increasing sequence, decreasing sequence, or either. Just keep going from left to right, and we keep track of, there's 3 possible states we could be in. or either part of an increasing sequence, part of a decreasing sequence, or either. And I'll go through code on the next slide to explain how this works. Now, another way to think about this is if you draw it kind of like a histogram. So I'll go through this solution in a bit more detail because there's code on the next slide, but first I'll do this one. So another way of thinking about the problem is, firstly, if you have two things of the same weight next to each other, they don't matter. In fact, I should have said this earlier. It doesn't actually matter what the weights are in the problem. All that matters is the comparison between adjacent pairs. So the ones where one is bigger than the next one or one smaller than the next one, that's pretty natural to handle. The case where they're adjacent, if you're ever going to push these over, you're going to push them over together because you're never going to push that one to the right because you could have just started from there. So you're always going to either knock them all over that way or knock them all over that way. So we can just kind of collapse them down into one. So once you've done that, which just makes it a bit easier to think about, then the answer ends up being 1 plus the number of local maxes plus number of local mins minus number of pairs of adjacent local maxes and mins. I'll quickly explain that. So if you draw it as a histogram, you're going to end up with some diagram like that. Now, what you can collapse is you can collapse along there, collapse along there, collapse along there, collapse along there, collapse along there. And so that means just from that, it's 1 plus the number of local maxes plus the number of local mins, because that will be the number of line segments in the broken line that I just drew. Now, this one is here because if you have a thingo where you're like 1, 2, 3, 2, 3, 4, you're going to have a histogram like this, which will have 3 line segments, but you actually only need 2 knocks, 2 pushes, because you don't need to actually do that one because these two are adjacent. So you can just knock over that part and that part. And since these two are adjacent, we don't actually need to do them together. So that's why we subtract the number of pairs of adjacent local maxes and mins. So whenever you have a thingo like that, dot, dot, dot there, and dot, dot, dot there, or dot, 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 then you subtract 1 from that count because we overcounted them. There's probably other ways to think about that as well, but that's a fairly nice calculation. I think it's right. I haven't actually coded that up, but I buy that it works. Okay, next slide, just for the code, quickly to explain that second solution, or the second point. So yeah, it should be fairly self-explanatory. 3 modes you can be in, either you're not decided whether you're increasing or decreasing or decreasing. So in this case, so you loop over and you keep updating your mode and your answer as you go. So all that matters is comparing it to the previous one. So if it's bigger, then you have to increase. So if it's bigger than the previous one, yeah, then it's increasing. So if you're undecided, then change it to increasing, and that doesn't cost anything yet. If you were decreasing before, then now you're undecided because you were decreasing and then you have to increase. So now you have to take that sequence and you can do whatever you want from here. It doesn't really matter. So that's why you mode 0 and you increment 1 for your answer because you have to switch direction. And this is just the flip of that. And the third case is if wi is equal to wi minus 1, and in that case, you just keep doing whatever you're doing. It doesn't actually affect it. So that's just kind of the way of collapsing in this case. But you can also just think of it as you don't need to change which mode you're in. And note that the answer is initialized to 1 here because you always have to do at least 1 push, I guess. And because that's kind of your base case of this whole sleeping idea. That's it for me from Dominoes, for Dominoes.
Okay. Then go back to Farmer Joe's. This is probably the last problem we'll go over unless there is sufficient demand to go over any of the other problems, just because the first 4 I think are easier. But if there is demand, we're happy to go over them too. So in this problem, you're given a grid of integers, and for each cell, its score is the sum of all cells that are not like kind of north, south, east, west, or the diagonals away from it. So if our cell is this one I'm circling here, then we ignore everything that's north of it. So we ignore everything north, that's these ones here, everything south, everything east, everything west, and everything diagonal, they get removed. And we sum everything else together, which are the green ones. And the question is, across all cells, what is the maximum possible score? In this diagram, I believe this one here happens to be the maximum possible score we can get. So we calculate the score for every cell, and we find the maximum one. So solution, the most obvious thing is just, well, we try every point as the center point and we calculate its score and then print the maximum one. That's just kind of rephrasing what the question's saying. So the question is, how do we do this efficiently? Well, one way of doing it, go back to the diagram, consider some center like this. We loop for each center, we loop over the entire grid. And to work out whether a cell is included or not, we check whether the row and column are the same. That's pretty simple. If we have like ij is our cell and AB is our other cell, we just want to check that A does not equal I and also B does not equal J, like that, to check if they're in the same row or column. Diagonals are a little bit more complicated, but if we number the cells like rows, like the columns like this and the rows like this, then we can define the diagonals. Well, if we consider this way diagonals, then if we sum together the row plus the column, that will be the same across diagonals. So for example, the big center diagonal is the case where row plus column equals 4. So all of these cells have that row plus column is equal to 4. All of these red cells I'm going to circle have it so that row plus column equals 5. All of these yellow ones, for example, have row plus column is equal to 2. And so to check if we share a diagonal, we check if our row plus column equals their row plus column. For the other diagonal, it's row minus column. So for example, the main diagonal the other way has row minus column equals 0. If we go up here, row minus column is equal to 1. If we go below in blue, row minus column is -1. And so to check if they're on the same diagonal, we check if the row plus column is and row minus column are different. That's going to be too slow. But to improve it, we have a slightly smarter idea. Rather than counting everything that is included, let's count everything that's not included. So for a given point, let's add together all of the bad cells. And then subtract that from the total sum of everything. And that will be precisely all the green cells added together. So to do that then, if we're smart and use like a for loop, for each cell, so for like this cell here, we do one for loop over its row, over its column, and for each diagonal, and we add them together. And this brings our solution down to about n cubed, because there's n squared possible cells, and there are n different cells or order n cells that we have to discount. But we can get even smarter than that, and we do some pre-computation. So for each row, we pre-compute its sum. So this first row, for example, I think we get 15. The second row, for example, we get 13. I could be wrong here, and we compute the sum for every row. Also, that's a column, not a row. That's my first mistake. But for every column, we pre-compute its sum. For every row, we also compute its sum. So this bottom row has 16. Then we have 9, etc., etc. And also each diagonal, we also pre-compute its sum. And then the value for this cell here, we add its row sum, we add its column sum, and we add the two diagonal sums. And then very finally, we subtract our value times 3. Why is that? Because we added our value 4 times. Once for the two diagonals, once for the row, and once for the column. So we go row plus column plus diagonal plus the other diagonal minus 3 times our value will be precisely all the gray cells. We then subtract that from the total and we get the answer. This is faster because we can compute the sums initially, and then it's just constant work for each row and column. So here's some code. Here, I have a bunch of arrays, and I pre-compute. So I have the total sum of everything. I then keep an array where I have diagonal 1 and 2. So diagonal 1 is this way, diagonal 2 is this way, and row and column. And I have an array where I compute the sum for each diagonal, for each row, and for each column. That's what's going on here. And then for each cell, the amount here is the total value. We then subtract everything and add our value times 3. It's inverted from before because remember, we're computing all the cells that are not in our row, column, or diagonals. So we add everything. We then subtract the diagonal, the row, and the column. And then we add back our value times 3 because we previously subtracted our value 4 times. And that gets the amount. And then we keep a running total of the best answer we have so far. And if our amount is better than the answer, we update the answer. And then we print the answer. And so that's solution to this problem. That's going to be fast enough. Any comments or questions? And is there any demand to go over any of the other problems?
Yeah, if anyone wants to go over any of the early problems or recap on any of these problems, I see we've got a question, or even just discuss the contest or anything, we're happy to do that.
Good question. I don't actually know. Does anyone knows the answer to that question? The way you can do it in C, which is not like a kind of dumb C way. What I end up doing. What you can do is you have an array of like length like 200 or something, and because you can use characters correspond to integers in like ASCII, and so you can use characters as array into C. So you can loop through your string and like add 1. So you can count how many occurrences of each character there are, and then check from there. Obviously, that's a bit of work, and it's probably a bit nicer just to use the library functions, which I think even C has library function, right? Dot find, but does C++ have contains? C++ check if string contains substring. Does dot find work? Is that a thing you can do? String dot find? Okay. String dot find apparently will work. Yeah, compare with dot end. Yep. So like it'll be like string dot find character. If that does not equal like that, where character is a string and not just one character, a character that's one string. Yeah. Does it? Oh, okay. Does it? Maybe. Okay. Dallas, can you send the correct syntax then? Does not equal string npos then? Okay. Some different syntax then. Yeah, all good. Yeah, something like that. C++ syntax can be a bit, some of that template syntax is a bit confusing, like the comparing with .end or with npos. Yeah. You know, that's reasonable. Switching to Python is often the smart way of doing it. For most string problems, switching to Python is the smart solution. I'm going to be honest there. Yeah.
If this is about the first problem in the contest, I think the code will, if you go back, the code will be there. It's like a few lines in Python. And it's probably fairly annoying in C or
yeah, this is some Python code. Yes, that's true. 4 and 2 8 in C++. Yeah, I also in C++, I use use C strings. Yeah. But here's some Python code for it. But yes, string can be annoying. Although generally 4128 doesn't have that many strings in it. There will be the occasional problem, I think. Yeah. Anyway, are there any more questions? Basic string manipulation is, I think, there isn't normally like super complicated. Like substring finding, I think, is fairly uncommon. Like there's the occasion, yeah, it's more right. Like the most advanced you might find is like, I don't know, finding palindromes or something like that might be a problem that you find. But there isn't normally that much advanced string stuff. Unless you're looking at like suffix arrays and stuff. Like there are out of the scope of 4128, out of the scope of most competitions, there's like suffix arrays, suffix trees, and those sort of things, which are more complicated string manipulation. Which do smart things.
I know that like the computer science of strings, I think, is like really, really deep. But yeah, usually you won't get asked about that. And whenever there's strings in competitions, usually they try and be nice.
Yeah.
Well, generally, at least that's my principle, and probably Angus's principle, is that it shouldn't be a hard part of the problem to work out how to get the strings working.
And it's like there's like
it was
string
a bit
hashing.
unfortunate that was the case with this question, but yeah.
Yeah. Like string hashing is also a thing which appears in some problems, which is annoying sometimes. But yeah, yeah. In this problem, this problem is just entirely like string manipulation, but most problems won't be that much string manipulation, I don't think. Are there any other questions? Okay, yeah, thanks. Any other questions about the contest? These slides are up on the CPMSoc website. Dallas, can you send the link in the chat? I think if you got it up. So if you want to see the slides, they're here. The recording will be, I think, emailed out and also on their website soon. That doesn't really apply to anyone here, I don't think. Oh, thanks. Yeah, I don't think that applies to anyone here since you're here, but anyone not here, the recording will exist hopefully later today. Yes. Thanks for doing the contest. That's all from me, I guess. Yeah, thanks everyone.